Okay, so picking up where we left off yesterday, okay, we were talking about how basically lots of sports science is focusing in on the fact that force multiplied by distance equals work, and that work is a change in energy, okay? We want to change the energy of things when we're playing different kinds of sports, be it golf or hockey or, you know, basically anything where you've got to make something else move, okay? This formula comes into play, all right? Obviously, athletic training is getting better and better and better, and so athletes are stronger and stronger and stronger than they used to be, okay? Hopefully not for the wrong reasons, okay? Hopefully because they train hard in the right way, right? So certainly the force that athletes are able to exert is getting better, all right? When we're talking about technique or equipment, that's where distance comes in. Okay, we talked about the hockey stick example and how composite sticks are far more flexible, which increases the distance over which a force can be exerted, enabling us to hit a hockey puck faster. Okay, if you're looking at kind of the simplest of all sports, okay, and I say that as a track coach, track and field is one of the simplest. You're either faster or stronger or higher than the other people. Okay, so if we're looking at things like, for example, like a shot put, throwing a shot put, okay, a lot of people who are just new to that just pick up the big heavy metal ball and throw it as hard as they can, okay, which is not a very effective way to do it because A, it's really heavy and that's hard on your joints, okay, if you don't know what you're doing. And secondly, they don't exert their force, even if they're very strong, over a very large distance, okay? And so a lot of technique has to do with increasing the distance over which you exert your force on the shot put. And if you ever see someone do it right, you notice that they are holding the shot put a lot longer than someone who's not, okay? So that's basically, if you're ever, doing a sport and they're, working on technique and they're really harping on what you're doing, it's because they're working on this part of the equation, even for something as simple as running. Okay, having an effective running stride means having your foot in contact with the ground at the right angle and for as long a distance as possible while pushing. Okay, simple things like that. All right, is that making sense to everybody? All right. Probably the most common example of the work energy theorem that we'll see in physics is the bow and arrow. Okay, when you draw back the string on a bow, what have you done? You've done work, because to pull back on the string would imply that you have exerted a force, and you've pulled it back, which would be a distance. Okay, so you've done work on the bow. When you did that, what did you do to the bow? You changed its shape. Okay, you pulled the ends of the bow closer together. Okay, so you can see here's the ends of the bow before it's drawn. Okay, but when you draw it, they're closer together. Okay, and the bow is usually made out of elastic material. Okay, in the days of Robin Hood, that was a piece of tree. All right, now it's carbon fiber, graphite, fiberglass, all kinds of synthetic materials that are way more elastic and have greater longevity than wood. Okay, so that's what we would use. We exert a force and we put elastic potential energy into the bow, because if we release that string after the draw, okay, then the string will move forwards, because the bow will try to return to its original shape. And when it does that, it exerts exactly the same force you exerted over exactly the same distance. Okay? Does it do it a little bit faster than you did it? Does that actually matter? It doesn't. Time isn't part of the equation that we were looking at. It's just force times distance equals work. Okay? So if I pulled back the bow with, let's say, 100 newtons worth of force, and I pulled it back 30 centimeters, okay, or 0.3 meters, right? How much work did I do? If I used 100 newtons of force to move it 0.3 meters. 30, yeah, 30. What are the units for energy? Joules. We haven't talked about that yet. Okay, joules are the units for energy. So I've done 30 joules worth of work. So there's 30 joules worth of energy in the bow. When I let the bow go, and that sounds terrible. Anyway, when I let it go, okay, the arrow flies out of the bow. How much energy does the arrow have? 30 joules. Law of conservation of energy. Okay, the energy I put into the system has to be conserved. It's not going anywhere else. Now, in the real world, would the arrow have all 30 joules? No, because a bow makes a sound when you release it, right? Okay, that's some of my energy going to what we call non-conserved forces, sound, okay, and things like that. Right? In the perfect physical world, all 30 joules would be transferred to the arrow, and off it would go. And then I'd be able to calculate how fast the arrow was moving, because I would know how much energy the arrow has. And what kind of energy would that arrow have? Kinetic. And we have a formula for that. As long as I know the mass of the arrow, I'd be able to calculate how fast the arrow was going. That's where we're headed. Okay? That's the kind of things we're going to be doing, okay, with work energy theorem. Using force and distance to calculate either kinetic energy or potential energy or something about that, either the height it is above the ground or how fast it's going, okay, or something like that. Does everyone follow? Okay? So more often than not, we're going to have force times distance equaling, okay, some form of energy, either kinetic energy or potential energy, or sometimes both. Because in truth, work is a change in mechanical energy, and we talked about how mechanical energy is both of those things. Okay, it's not very often that you would have one with both. We save that mostly for physics 20. In science 10, we deal with one or the other. Okay, all right. Force and acceleration. So a force is exerted, okay? That can cause a change in energy. But what is force? Well, force is a push or a pull, very simply. Okay? That's all it can be, a push or a pull. All right? There's contact forces, like if I walked up to a desk and pushed on it, that would be a contact force. Okay? If I tied a rope to the desk and pulled it, that's a contact force. Friction's a contact force. Things have to be in contact for forces to be exerted. Okay? There's also field forces. All right? Do I have to be in contact with the Earth to be pulled towards the Earth by gravity? Nope. Okay? The moon isn't attached to the Earth, okay? But it's still attracted to the Earth, okay, by gravity, because gravity is what we call a field force. It's a force that does not require two objects to be in contact with each other. Okay? Electrical fields, magnetism is a field force. Okay? We can attract things by magnetism or repel things by magnetism without them being in contact. We don't deal with field forces in Science 10 at all. All right. Force is mass times acceleration. That's what this formula is saying. This formula is on your formula sheet. Okay? We don't use it very often. In fact, I don't remember us ever using it, but we still go over it. Okay, it's important to know what force is. So, strange diagram, I'll give you that. Guy with a golf club, going to use it in the proper fashion. Okay, he's going to exert a force, which is based on his strength and technique, okay, on a very small mass, the golf ball. When he strikes the golf ball, he's going to produce a very large what? A very large acceleration. Okay? That's what the A stands for. He's going to produce a very large acceleration because the mass is so small. All right? Will the ball have a lot of kinetic energy? Actually, it probably won't because it's very small. Okay? It might be moving very fast. V might be very big, but M is going to be very small. Remember that kinetic energy is 1/2 mv squared. So just because something's moving really fast doesn't necessarily mean it's got a whole lot of energy. Okay? Charged particles come here from the sun moving at pretty much the speed of light, and they don't hurt us. Right now, you're being hit by photons, okay? Little particles of light that come from the lights. They're moving at the speed of light. Thankfully, they have practically no mass, so we don't feel them. Otherwise, sitting under lights would be a very uncomfortable situation. It would be like standing in a hailstorm. Okay? Not fun. All right? So if they don't have very much mass, mass is part of this. Okay? They don't have very much energy then. All right. So Second situation. For some reason, this golfer is going to wind up and smoke this truck with the golf club. Okay? So, same force because it's the same guy and the same club, but now we're hitting a very, very large mass and we're going to produce a very, very small what? Realistically, is the truck going to move? Okay, probably not. Right? If this was the perfect physical world and the truck was sitting on a perfectly frictionless surface, then the truck would move. The reality is that's not going to happen. Okay? Does that mean that he doesn't accelerate the truck? If I was to be standing at the front of this truck, I'm a lot skinnier in that picture, okay? And I have my hand on the truck. Will I know when he hits the truck? Sure it will, because the vibration will travel through the truck when he hits it. I'll also hear him hit it. I'll probably hear him curse and swear because it'll really hurt, okay? But yeah, I'll feel the vibration pass through the truck. So maybe the whole truck doesn't move, but do the particles that make up the truck move? Yes. Okay? And as a result, there's an acceleration. They just didn't move all in the same direction at the same time. A vibration passed through them, which passed to the front of the truck. Okay? Still counts as an acceleration, especially since there will also be a dent back here, okay, where he hits the truck. Okay? And that's a change in shape. All right. So that leads to this. Motion does not just mean the object moves from one place to another. Okay? When an object is compressed or stretched, the atoms within it are moved. Okay? In the same way that when the truck vibrates, the atoms within it are moved. Okay? So the changes in the shape of an object constitute an exertion of force. Okay? And thus they result in work and energy transfers. Okay? If I had, like something that could measure vibration attached to the truck, it would move. That would mean that energy was transferred from the golf club to the truck to the measuring device. Okay? And the only way that could happen is if energy moved through the truck. Okay? Everyone's okay with that? Right? It's the same thing with this spring, right? If I compress it, right, I've moved the atoms closer together or done something with them. I've rearranged them somehow and that they're not in the same way they were before, and they're going to want to go back to the way they were. Same if I stretch one. Okay? A change in shape still counts as movement. All right, questions on that? Okay, so work and heat are transfers of energy. Okay? Remember that heat is a transfer of what kind of energy? Thermal. Work's a transfer of mechanical. All right, so okay, so when the molecules of two objects originally at different temperatures come in contact with each other, that's thermodynamics. Okay, that's the second law of thermodynamics. Energy always flows from hot to cold, high to low. Okay, transfer of thermal energy is called heat. Okay, so heat's a transfer of energy. All right, on that. So that's just a quick review because we've already talked about that. We talked about that the very first day. All right, potential energy. You have it if by your either chemical nature, position above the earth, or elastic nature, you could have potential energy. Okay? We're going to deal with in physics, at least in Science 10, almost entirely with gravitational potential energy. We'll once in a while talk about elastic. We're never going to do anything about chemical because that's mostly a thermal thing. Okay? So, gravitational potential energy is something you have if you have the potential to what? Fall. Okay? If you have the potential to fall, you have potential energy. Something lying on the ground has no potential energy. Okay? Now, let's think about a couple of hopefully not real world situations. I think I used this example once before, but I'll say it again. Perched precariously on the edge of a building are two objects, a penny and a piano. You have to stand under one of them. Which one are you going to choose? The penny. Why? Okay, why won't it hurt? It'll probably still hurt, but it won't kill you. Okay? It's not as big, right? Mass matters. Okay? Potential energy is affected by three things. The object's mass. The acceleration due to gravity, which on Earth is always the same number. What is it? 9.81. Okay, and how high the object is. Okay, now, if the piano was this far off the ground and the penny was at the top of the building, would your choice possibly be different? Yeah, because you couldn't stand underneath the piano then. It's only a centimeter off the ground. It can't possibly hurt you. Okay? Well, I suppose it could if they squished you under it. But, okay, we're not going that far. All right? So, certainly, yeah, how far something falls is going to be a pretty big determiner in how much energy it's going to have. Agreed? All right. Does any of these have more effect on potential energy than the others? Okay, when we looked at kinetic energy, we said that V had a much greater effect than M because V was squared. Are any of those numbers squared? No. So a change in any one of them will have an equal effect. If I double the mass, I'm going to double the energy. If I double the height, I'm going to double the energy. If I somehow doubled the acceleration due to gravity, maybe by going to a heavier planet, I would double the potential energy then. Okay, that's kind of the one that doesn't really change for us because we don't do too many calculations for potential energy on other planets. Okay, all right. Situation. Okay, one person is pushing this block. Let's say it has a. Let's say both of these blocks are 50-kilogram blocks. All right, that's just over 100 pounds. So that guy's pretty impressive. Okay, because he's lifting that right over his head. Who does more work if they both end up at the top of that ramp? Okay, let's say, I like where your head is at. Let's say it's a frictionless ramp. No, but I like that you brought potential energy into that because it got something to do with it. Hey, you're on the right track. That's why the ramp, the inclined plane, is the simplest machine. It makes work easier. But does it make less work? Yeah, it's the same. They both do the same amount of work. Okay? The blocks are the same. And when they get to the top of this ramp, they will have the same mass, the same gravitational potential, or the same acceleration due to gravity, and they'll be the same height above the ground. Okay? Getting to the top of this ramp requires the same amount of work, regardless of how you get the box there. Pushed it, pulled it, lifted it. Doesn't matter. When it gets to the top of the ramp, it has the same amount of energy. Okay? Now, the other explanation. Work is force times distance. Who has to go further? This guy or that girl? The girl. And who has to use more force? The guy. So he's got greater force, smaller distance. She's got less force, greater distance. But in the end, they do the same amount of work because the energy of the block changes by the same amount, regardless of how you get it there. Okay? Everyone follow me on that? Okay? That's the whole reason behind the inclined plane. The inclined plane does not make you do less work, but it makes that work easier because the plane supports the weight of the block. This guy's got to support the entire weight of the block when he's moving it. She doesn't. She can use a lot less force, but she's got to exert that force over a greater distance. All right? That's how the Egyptians built the pyramids. They did not have help from aliens. Okay? They had two resources in great supply, slaves and sand. So you make really, really long ramps, and you have lots and lots of slaves push big bricks up the ramps. Okay? By the time they were at the top of the pyramid, the ramps could have been several miles long. Okay? Because you imagine the pyramids are pretty tall. And it's not like you can make the ramp like this. Okay, then you probably don't have enough slaves to push the rocks, okay, up that steep of an incline. Okay, the incline would have been like less than 10 degrees. Okay, very small incline. Making sense? That's a weird one. People sometimes have trouble getting their heads around that. Okay, but it's true. Okay, don't let yourself become an inclined plane wrapped around an axis. Daniel knows what I mean. Don't let yourself be screwed, because that's what an inclined plane wrapped around an axis is. That's why screws work the way they do. It's way easier to put a screw into wood, okay, than a nail, because the threads on a screw are a ramp. They go around. They allow it to pull itself in. Yeah, it's a Sheldon Cooper joke. It's from Big Bang Theory. Okay, he said to him, "Well, you're an inclined plane wrapped around an axis. You're screwed." Oh, and I laughed for like 10 minutes. My wife was looking at me like I was a crazy person. Anyway, it's because I do a lot of stuff with inclined planes in Physics 20, so it seemed funnier to me. Okay, looking at this situation here. I've got this hanging mass that has a mass of 5 kilograms, and I have a 3 kilogram block that's sitting on, let's say, a frictionless table. Okay, how much energy, potential energy, does this system have? Where's the energy coming from to make this system go? From this. This doesn't have any potential energy, does it? It's on a table. I mean, technically it's on a table. It could fall off the table, but it can't fall off the table, so it doesn't have any potential energy. Okay? This, however, is 2 meters above the ground. Okay? Does it have potential energy? Because it's just hanging there. Okay? Can I calculate how much it would have? Yeah. So I would go 5 times 9.81 times 2 meters. So 49.05 times 2, so 898.10, not newtons, joules. Okay, I should not do math in my head, that hurt. Okay. It's going to diminish some of the force, yes. It's not going to diminish any of the energy. That's right where I was going. Thanks, Daniel. Okay, so it's when it hits the pulley, it's going to fly over the pulley. We're only going to deal with the here to there. Yeah? Before destruction occurs. Okay? Because then the system kind of breaks after that. So in this short range here, let's say that it could actually fall. Let's say that this is 2 meters from the pulley. So when this thing hits the ground, basically it's all over then, right? Okay, so when this falls, it's going to convert its potential energy into kinetic. But it's not going to get all of the kinetic, all of this 98.1 newtons is not going to stay here, is it? Some of it's going to be used to change the energy of this block. All right, so 2 parts of the system are going to move. When this is all done, does the system in total still have this much energy? Yes, it does. It's just not all in that round ball anymore. Some of it will be kinetic energy of the blue block, and some of it will be kinetic energy of the moving ball. Does everyone follow me there? Okay, they'll split it. Okay, but it's all still going to be in that system. That's what we talked about the first day when we talked about the different kinds of systems. Okay, and we said the energy of an object or system is always conserved. Well, this is an example of that. This energy has got to be used to move this as well as that. Right? And that's something that we work on in Physics 20 a little bit, doing the actual calculations of how much will each one of them have, how fast will each of them go. Well, the final answer is they each have to go the same what? Can one of those items move faster than the other? No, because they're attached. Okay? It would be like saying a truck pulling a trailer, the trailer can go faster than the truck. Well, hopefully you have proper brakes. If you stop the truck, hopefully the trailer stops too. Otherwise, you jackknife, right? Yeah. Okay, so the answer is that these would both move at the same speed. But which one would have more energy if they're moving at the same speed? This one, because it has more mass. Okay? The whole system still has the same amount of energy. All right, as long as we're good with that, we can move on. All right. Okay, so we've talked about this already. Okay, potential energy is mass times gravity times height. Important thing here, units. Obviously, energy is always in joules. In physics, we deal with big things, unlike chemistry, which deals with small things. Chemistry, mass is always measured in chemistry, we measured it in grams. When we did the mole equation, it was always grams and grams per mole. Physics, we go big. Mass will always be in kilograms when you're doing your calculations. Okay, it has to be because joules are really a kilogram meter squared per second squared. Aren't you glad we use joules? Okay, but that's technically what they are. So our mass has to be in kilograms. Okay, our distances have to be in meters. Okay, and time's always going to be in seconds if it's part of it. Okay, so g is the acceleration due to gravity. Okay, and h is the height above the ground, always measured in meters. Okay, everyone good with that? Questions there? Okay. All right, so simple example here. If I take a 3 kilogram box and I lift it 1.5 meters above the ground, okay, what's the potential energy of the box in the new position? Okay, so potential energy is m times g times h. Do I have to manipulate that formula at all? Is it already set up to calculate E? Already set up. So all I got to do is plug in the numbers as they've done right here. 3 kilograms times 9.81 meters per second squared times 1.5 meters. That object has 44.1 joules of potential energy. How much work did I do? How much? Yeah, how much? How much work in joules did I do in lifting that thing to the top of the table? 44.1 joules. Because remember, work is a change in energy. How much energy did it have on the ground? 0. How much energy does it have on the table? 44.1. Remember, change in energy is final energy minus initial energy. Okay? 44.1 minus 0. Okay? And see where we're going here? I'm not trying to oversimplify things. I just wanted you to see the connections there. Okay, second example. Sometimes we got to manipulate. This is a really easy formula to manipulate because everything is being what? Multiplied. So if I want to move anything, I just divide it over the other side. So it's nice and easy for manipulating. Okay, if I want to solve for how high this diving platform is that this diver is on, when they're on the platform, they have 5,400 joules worth of energy. Okay, and they have a mass of 55 kilograms. So I manipulate E equals m times g times h for h. So I just divide both sides by m times g. Okay, and that leaves me with h. So we just plug in our numbers here. Okay, 5.40 times 10 to the 3 divided by this. And this would have to, of course, be entirely enclosed in brackets on the bottom. Otherwise, your calculator will do order of operations, and you don't want that. Okay. All right. So, anyone ever jumped off the 10-meter diving platform? Yeah? Okay. They have like lots of like university pools and stuff have the really tall platform. Yeah. Like it feels like someone has slapped you really hard when you hit the water, okay? Because the water has slapped you really hard when you hit it when you fall from 10 meters. Okay, it's a long way down. Okay, another quick question here. We said that work is force times distance. What force are you working against when you lift something? Gravity. Okay, look on your formula sheet. On your formula sheet, is there a formula that calculates this? M times g. The force of gravity is mass times the acceleration due to gravity. Okay? So if work is force times distance, and I'm working against the force of gravity, when I calculate the work, I'm going mass times gravity times distance. that's where that formula comes from. Is a vertical distance also called a height? Yeah. Okay, so that whole potential energy formula is really just that formula. Okay, just manipulated to have the stuff in it. All right. Kinetic energy is the energy that really gets things done. Okay, you can have all the potential energy you want, but it doesn't do anything. Okay, potential energy just converts into kinetic energy, and then work gets done. Okay, so anyone ever watched people break stuff with their hands? We are going to watch it. Okay, I've got a couple of cool ones on here. That show people doing work using kinetic energy. Now, there's a lot of obviously technique and practice that goes into being able to do this. You or I cannot walk up to a stack of 30 sidewalk blocks and go like this and hope that they are going to split down the middle, and we're not going to have a compound fracture. Okay, so there's a lot of technique and there's a lot of practice and training that goes into that. They had this thing on the Discovery Channel about 6 or 7 years ago now, where they showed what happens to the bones of people who do this stuff. And it didn't show them breaking. It's microfractures. Every time you exert a force on your bones, even just walking, okay, because your bones are made of tissue and cells, okay, there's little tiny microfractures that always occur. But then your body repairs those microfractures and they come back stronger. Okay, the bone density on people who do this stuff on a regular basis was insane. Okay, it was way more dense than that of a normal person, simply because they do it all the time, and their bones are constantly repairing, and the matrix that makes up their bones was so incredibly complex and interwoven and dense that their bones were really, really strong. Okay, if you or I were to walk up to one of those, even if we had the technique right, we'd probably still get a compound fracture. Okay, simply because our bones aren't essentially prepared for that kind of an impact. Yes, one without the other is not good, because strength just moves your bones. Okay, you can have huge muscles, but if your bones are weak, normally those don't go hand in hand. You don't usually get big muscles without also getting increased bone density. Okay, because usually you get big muscles by lifting heavy weights that cause microfractures and etc. Okay, but yeah, certainly that would be a problem. If you had super strength and not super bones, you could hurt yourself really badly. Okay. Now, this is also a problem, this bone density thing, for the astronauts that live on the International Space Station. Can you constantly be causing microfractures in your bones if there's no gravity to cause impacts? Yeah. Okay. When Chris Hadfield came back from the International Space Station, this is what all his research was on. This was the bulk of his time on the International Space Station was spent doing essentially research on the long-term effects of living in zero gravity on the human body. When they came back, they had lost 30% of their bone density. They were essentially as frail as an elderly person. Okay, their muscle tone was actually pretty good because they had, they have like a Bowflex up there, okay, which allows them to work their muscles, but not in the same way that real weight does. Okay, because you don't take a weight bench up to the International Space Station, right, for a couple of reasons. The first reason being weight is expensive when you're trying to launch things into space. The heavier things are, the more money it costs because the more fuel you need and the less stuff you can put on. Okay, the second thing is you'd have wasted all of your money because weights don't work. Right? So you'd set up the bench on the International Space Station, put like 5 plates on that bar, okay, get underneath it, go like this, right? And it would be nothing because it doesn't have any weight. Problem, once you get it to here, no gravity. Okay, it would just take off and take you with it. Okay, once that weight gets moving, there's nothing to bring it back. Okay, it would just jerk your arms right out of the socket. Okay, and pull you off of the weight bench, which would also be floating there. You see the problem? Doesn't work. Yeah, weights don't work in space. Okay, you have to have like this. You have to have all kinds of resistance type stuff. They have the coolest treadmill and stationary bike. There's like this life preserver thing that goes around your waist, and you're bungee corded onto the treadmill because you can't run in zero gravity. So the bungee cord keeps you on the treadmill, and you kind of bounce on the treadmill. Okay, so things like that. But it's not the same as doing it in real gravity. So their bones got really weak. Okay, and it took them a while to get strengthened up again when they came back. Now they were young, healthy individuals. They were able to do that, but if you were in space for 6 months on your way to Mars in zero gravity, and then you got to Mars and I mean, it's a third gravity on Mars, you'd probably be okay. But when you return to Earth after being in zero gravity, 1/3 gravity, and then zero gravity again, you could be pretty frail, okay, by the time you came back. So there's some issues with that. All right, we'll show you a couple of videos here. Okay, so that's where we're at with kinetic energy. Kinetic energy is essentially the energy that really gets things done. Okay, and there's lots of different kinds of examples of kinetic energy. Okay, simple things like when you hammer a nail into wood. Right, the hammer has kinetic energy. In case you haven't tried it, just setting the hammer on the nail will result in nothing. Right, because the hammer doesn't have any what? Doesn't have any energy. It's not moving. Okay, it can't do any work if it's not moving. All right. Moving molecules in hot steam can turn turbines. Okay. Moving molecules in a sound wave make your eardrum vibrate. Wind. Okay. I mean, right now in this room, are all the molecules of air in here moving? Yes. Are they moving in the same direction? That's why it's okay. Okay. They're all moving completely randomly, so we don't notice them. But if all the molecules of air in this room started moving in the same direction at the same time, we would call that wind, and we would feel that. Okay? Even though each individual molecule is very small, a lot of air gets moving. It builds up a lot of kinetic energy. That's why wind can do a lot of damage. Okay? There's a lot of air out there. Okay? And if you get enough of it going in the same direction at the same time, okay, it can knock things over. All right, is that making sense? Okay, sound waves, similar deal. Okay, that's just particles in the air. They're not moving from A to B, but they're vibrating back and forth like this and causing other molecules to vibrate back and forth, and that makes your eardrum vibrate back and forth, right? And the further it vibrates, the louder the sound appears to us. Okay, is it possible to do damage to your ear? Yeah, okay, if you're listening or exposing your ear to sounds that are very, very loud, especially if you're doing that on a regular basis, the little bones in the middle of your ear, okay, the hammer and the anvil and the stirrup. You guys remember those from like grade 3? Okay, okay. So those are the bones in the inner ear. They're connected just like any other bones in your body are connected through tendons and ligaments. Okay, it's just like any other joint in your body. If you cause them to move radically, okay, they'll injure themselves, or you will injure them. Okay, in the same way that if you make your knee or ankle or shoulder or elbow move in a radical fashion, okay, you'll injure it. And then what does it do after that? If you injure something, sprain your ankle, something like that, what does it do? It swells up, right? Well, same thing happens in the bones of your inner ear. Okay, the little ligaments and tendons that connect them get stretched, they swell up. And then the bones in the ear, because there's extra fluid in there, move around more freely as you move. And you hear a ringing sound. Okay, tinnitus, the ringing in your ears. If you've been to a concert the next day, right, and your ears are ringing a little bit, it's because you have caused, and I'll say this, irreparable damage, okay, to the inner ear. The more times you do it, the more scar tissue builds up, same as you would in any other joint in your body, okay? And that scar tissue builds up, the ability of those bones to move decreases. And what do you lose? You lose your range of hearing. Okay? Every time your ears ring, you hear a little less. Okay? Every single time your ears ring, you're going to hear a little less. You're not going to notice it, not right away. Okay? But as you get older, okay, it starts to compound. It gets worse every single time. Okay? Until you're, needing maybe even hearing aids. You're going to be your generation that's going to be the worst. Okay? You guys are the iPod generation, right? You guys use headphones more than any other generation ever has before you, okay? And headphones are, if you crank them up, right, you seal them in there and you don't allow a lot of movement of air to come in, and so you get a lot of extra movement of the eardrum, okay? And it can cause a lot of damage. So you'll want to hear your children laugh when you have them. That's the most beautiful sound in the world, hearing your children laugh. Okay, so make sure you can do that when the time comes. All right. I'm not saying rush into having kids. I'm saying protect your hearing. Okay. Yeah. All right. Okay, so kinetic energy, like we said, is energy due to motion. If we look at a roller coaster is another prime example of mechanical energy, okay, that we'll deal with all the time in this course. Okay, if I'm up here at the top of the first hill on a roller coaster, you're rolling, but you're not rolling very fast. But you're very what? You got a lot of potential. You're very high off the ground. Now, as you go down the hill, your potential energy goes into kinetic energy. So your potential decreases and your kinetic increases. All right, perfect physical world. Here I have 1,000 joules of energy. How much do I have down here? 1,000. What's different is more of it is potential up here, more of it is kinetic down there. All right, but I have the same amount of energy in both places. That's the law of conservation of energy. Okay. All right. Okay, so this is the formula we were talking about here. EK equals 1/2 mv squared. Okay, so the kinetic energy of an object is influenced by its mass and its speed. More so by its speed than its mass, but mass is still important. Okay, everybody with me there? All right, how many of you have taken or are going to take driver's ed? Okay, here's something that all of you will need to hear because they don't teach it to you in driver's ed, even though I think it's the first thing they should teach you in driver's ed. Okay, if I'm traveling in a playground zone, let's say I'm going the speed limit, okay, what kind of energy do I have? Kinetic. I need to stop suddenly. What do I need to do with that energy? Yeah, well, it's hard to stop energy, but I need to waste it. Yeah, I need to get rid of it. I need to make it turn into something that doesn't involve me moving forwards anymore. How does your car do that? Right, your brakes clamp onto the rotors, okay? And when they do that, they turn your kinetic energy into heat and maybe a little bit of sound, all right? But mostly heat. I need to turn all of the kinetic energy I have into heat, all right? I need to change my kinetic energy. What do we call a change in energy? Work, all right. Work's a change in energy. How do I calculate work? Force times distance, okay? And change in energy is final energy minus initial energy. What do I want my final energy to be? 0, I want to be stopped, okay? So really, if this number is 0, the work I need to do is really just equal to EI, right? Everybody okay with that? I'm negative EI because the object's losing energy, but we don't really need that part in there. Work is scalar, so, okay? All right, so basically, the force multiplied by the distance has got to equal the kinetic energy I have the instant I slam on the brakes. Everybody okay with that? Right? That's essentially what we have to do here. We want to turn our kinetic energy into heat. That's going to involve work. I've got to change my kinetic energy. All right, let's put some numbers in here. The force that my brakes can exert through friction between my tires and the road is, let's say on average, about 8,000 joules. Or sorry, 8,000 newtons, not joules. 8,000 newtons worth of force. Okay? That's how much force my brakes can exert. Okay? Average size car. Let's say the mass of the car is 1,500 kilograms. How fast can you go in a school zone? 30. Okay? Got to convert that to what? Can I use kilometers per hour in this? I need meters per second. So 30 divided by 3.6 is going to give me 8.3, I think, right? Can someone just punch that in real quick? I think it's 8.3 repeating, if I recall. Just someone punch it in and confirm. Okay, 8.3 meters per second. Okay. I want to calculate how far I'm going to travel before I stop. Do I have everything I need except D? Okay, D is how far I would travel. Agreed? All right. How do I get D by itself? Divide F, right? All right, so I'm going to calculate how far I would travel if I'm going the speed limit, okay, with a 1,500 kilogram car. All right, so I'm going to have 1/2 times 1,500 times my speed, 8.3 repeating squared, divided by the force my brakes can exert, 8,000 newtons. Okay, so 0.5 times 1,500 times 8.3. Okay, and then I'm going to divide that by the force that my brakes can exert. All right, so I would travel 6.5 meters. So from my desk that far. Okay, and that's going the speed limit, mind you. Okay. Yeah, there would also be reaction time. Let's say I'm incredible. I hit the brakes the instant I realize there's a small child running in front of my car. Okay. All right. I would travel 6.5 meters. Now, what would happen if I was going faster than that? I'd go farther. Linearly farther or exponentially farther? Exponentially farther. Okay? How much faster than the speed limit do most people drive? Yep, usually about 10 kilometers an hour. And you know what? We all do it. And we go, that's just 10 kilometers an hour. Okay? Well, we shouldn't do that. Okay? Because speed is exponentially related to your stopping distance. So, let's say we're going 40 kilometers an hour instead of the speed limit, which is 30. Okay, so is that going to be what, 11.1? Can someone just punch that in? 11.1 repeating. Okay. All right, so instead of going 8.3 meters per second, I'm going to go 11.1 meters per second now. Okay, just 10 kilometers an hour over. I'm just going 40. 40 is not all that fast. Okay, so 0.5 times 1,500, still the same car, okay, times 11.1 squared, okay, gives me that, divided by 8,000 newtons. It's almost double. It's longer than this room. In fact, it's almost to the other side of the hallway. It's 10 kilometers an hour. It's almost double the stopping distance. Okay? That's why there's zero tolerance for speeding in school, playground, and construction zones. Okay? Your speed is exponentially related to your stopping distance. I have no idea why this is not taught in driver's ed. I think the math intimidates people, but the math is not very difficult. Okay? The faster you go, the farther it takes to stop exponentially. That 10 kilometers per hour, okay? Well, it's what? 3 meters per second. Okay? It's 3 meters per second through a playground zone, okay? Or a school zone. Let's say the school zone is 300 meters long. How much time did you save? 10 seconds. You saved yourself 10 seconds. But if my kid runs out in front of you, that 10 seconds that you saved costs me everything. Think about it. Sometimes physics sucks. That's one of the situations, okay? But it doesn't lie either, okay? So don't go 10 kilometers an hour over the speed limit through a school zone or a playground zone, because the 10 seconds you save is the difference between me having dinner with my sons or not ever again. It's a big deal. Yeah? Okay, what if I was stupid, double the speed limit, 30? What if I went 60? What's going to happen to my stopping distance? How many times greater will it be? If I double my speed, I'm going to need 4 times as much distance to stop. Okay, I'm going to need over 30 meters to stop if I go 60, because it's exponential, right? 2 squared is 4. 4 times the distance to stop. Okay, if we just do that, okay, 8.3 doubled 16.6. Okay, so we go 0.5 times 1,500, not 15,000, sorry, not divided, times, okay, 16.6 repeating, squared, divided by the force my brakes can exert. 26 meters. It's a long way, right? It's like a tenth of the school zone. It's a long way. Think about it. Be a responsible driver. Yeah, you'll appreciate it when your kids are old enough. Okay? That's why some people have those like fluorescent yellow signs that they put out in the street in the summertime, right? You ever seen those slow down children playing signs? Because people are idiots. Oh, was that out loud? Okay, they are. They're just we're by our nature very self-centered, and I got to get there. I got to get there, and you're whipping through a zone that's 40 at 60. Okay, well, if you're whipping through a zone that's 40 at 60, you're taking exponentially more distance to stop. Okay, I know the street I live on is horrible for that. It's a very straight road, and the speed limit is 40, and I have seen people cooking down that road at 80. Okay, like it's nuts. That's why actually they changed all the speed limits in town. Okay? Did you guys read that? That was in the paper the other day, right? Basically, all residential streets, unless otherwise marked at 30, are 40. Okay, there are a few residential streets that are 30. Okay, but all residential streets are 40. Okay, South Ridge and North Ridge Drive are 50 until you get up to Milligan Drive, and then it is 60 until you get to 338 out here. Okay, where the Honda and Chevy dealer is there. Okay, then it's 100 after that. Right? So they've changed all the speed limits to slow people down. It's Okotoks thing, yep. Just Okotoks, so a local traffic enforcement. Because there has been, I know there's been lots of complaints about speed in town. A lot of people are going way too fast. Okay, something to think about, food for thought. Okay, practical application. Oh, see there, I saved it from the last time I did it. I didn't need to put a new slide up. See, I remember the numbers even. Okay, so which has more kinetic energy, a semi-truck moving at 30 kilometers per hour or a bike moving at 30 kilometers per hour? Semi-truck because of its mass. Okay. Yeah, we've talked about the other ones already, so we'll skip over those. All right, I want you guys to try this example right here. I'm going to give you a few minutes to try it, and then we'll go through it together. Okay, first thing we want to do is write down our givens. Okay, same as any other problem. Okay, rubber band is stretched 0.85 meters. So what did they give me there? Distance. Okay, by a force of 60 newtons. Force. All right, I've got force and distance. Right now I could already calculate what? Work. So that's probably part of this. Okay, other things I'm given. At what speed? So I'm looking for V. Okay, would it propel a 0.125 kilogram ball when released? Okay, so speed deals with what kind of energy? Kinetic. And there's obviously work being done here because the rubber band is being stretched. Will that stretched rubber band change the kinetic energy of the ball? Yes, it will. Okay, if I put the ball in the rubber band and pull it back like this, okay, then it's going to shoot it out when I release it. That means that the work I do in pulling it back is going to become the kinetic energy of the ball. Okay, we talked about that with the bow and arrow. This isn't any different than the bow and arrow example. Okay, if I do work, That energy is in the ball rubber band system now. If I release the system, then the system will do work on the ball, and the ball will fly out of the system at whatever speed. All right, so work is a change in energy, all right? And work is force times distance. What kind of energy did we say the ball was going to have? Kinetic. Okay, ball's going to have kinetic energy because they're asking about speed, and speed's part of kinetic energy. So we're going to have 1/2 mvf squared minus 1/2 mvi squared. Is that just ef minus ei? Is that what I've written there? The final kinetic energy minus the initial kinetic energy. Everybody okay with that? All right. How fast is the ball going when it's in the rubber band back here stretched? 0. So what's its initial kinetic energy? Okay. I have everything in that formula now except for V. I have m, I have f, and I have d. Can I solve for v? Yep. Okay. So how do I get v by itself? Divide by 1/2 of m. Yep. And then what? Square root. Yeah, v is squared. I don't want to find v squared. I want to find v. Okay? That's the bulk of what work energy theorem is going to be like for you. It's going to be setting work equal to either kinetic energy or potential energy if this is something moving vertically. Okay? So now I plug in my numbers. All right, so the force was 60 newtons times the distance, 0.85 meters, divided by 1/2 times 0.125. Got to do the top before the bottom. Okay, they kind of have to be in brackets there. Okay, so when I punch this mess into my calculator, there's 2 ways to go about it. You could do it with lots and lots of brackets. So, actually I need 3 sets of brackets. No, I don't. All right. 60 times 0.85 in bracket divided by 0.5 times 0.125. What's that? Oops. Good catch. 28.6. The other way you could do this would just go 60 times 0.85 equals that, okay, divided by 0.5 times 0.125, and then square root. I did 6 again, okay, but then square root that answer and you'll get same thing. Okay, so you can do it piecemeal or you can do it with all of it plugged in at once. Okay, comes out to 28.6. All right, all work energy theorem questions work the same way. Set the work equal to the energy that's changing, solve for what you're looking for. All right, we'll work on that a bit more tomorrow. Okay, tomorrow is Thursday. And I'm going to post a quiz. It's going to be on acceleration, though. Okay, it's not going to be on this stuff because we haven't gone into it enough yet. All right.